Yeah.
I don't know if it's even one factor.
So I'm going to start class, work in a few examples, and so I want to talk about something, and I don't know if this is actually quite tested in your homework. It was going to figure into Lab 6, but I deleted Lab 6. But I just wanted to spend a little bit of time talking about this because it's an important concept. And the basic concept is this. The definite integral is used as a quote-unquote continuous sum. All right. Now, so what I mean by this is that if you can set up the calculation of some quantity in terms of a finite sum, all right, and then as you pass to the limit, that finite sum becomes a definite integral, well, that's what we call this infinitesimal method. Now, that said, if you read any like calculus book, like the one I've recommended for this course, Stewart, you'll find in there that he sets up these summations, and he takes the limit as n goes to infinity, and then the summations become, integrals. So I'll let you look in a standard book if you want to see that. But what I'll show you is a somewhat more heuristic method where we set up a typical infinitesimal version of the sum, and then we integrate to add up the infinitesimals. All right, so let me illustrate by example here. So example 1, we have y equals f of x, right? And suppose we want to, calculate the area from A to B. And let's suppose that f of x is non-negative, greater than or equal to 0. So the first and kind of like sort of simple version of this idea is, okay, so if I want to calculate the area under from A to B of f of x, y equals f of x, what I can do is I can draw a typical, so-called typical infinitesimal approximating rectangle. All right, so what that looks like in this case, and I never can quite draw it infinitesimally, right? So my infinitesimal pictures are always way, way too big. But you can think about the width of this box being dx, and what's the height of the box? It's y, right? It's, in this case, which is equal to f of x, right? So, and what's the infinitesimal area for this rectangle? Well, the infinitesimal area, it's just the length times the width, right? Which in this case is f of x dx. So this is the infinitesimal relation. That's how a little bit of area relates to a little bit of dx, right? And then the concept is to find the total area, we just integrate. So we integrate both sides. And so this integral is equal to that integral. And you have to, okay, so this is going to give us the total area, right? And on the other side, to be reasonable, we have to integrate over the appropriate range of x, which here is A to B, right? So, of course, we have talked about this before, right? This is the basic application of the definite integral, but I wanted to show you how we can also understand it from this infinitesimal method. Yeah, the dx, right.
And the dx is from A.
Yeah, x exactly. This approximating rectangle we can draw from a less than or equal to x less than or equal to b. Now, let me just show you, to be technical and to be precise, what you should do is something like, a is equal to the sum, j equals 1 to n of f of x sub I, x of j star, or we could just use x of j times delta x, right? And that's like the nth approximation, right? And then we say, oh, okay, well then take n going to infinity, and we get a is the limit as n goes to infinity of this summation, right? But then you're like, oh, but I know what that is. This, by definition, is the integral from a to b. So like this is what you'll find in calculus books, is they'll set up the finite approximation of the thing you're calculating, and then they'll take the limit as n goes to infinity. But for practical purposes, I think it's a useful, and at least in physics and in engineering, we like to use this infinitesimal method to just bypass this altogether. We just go straight to the concept of a continuous sum. So example 2. Do you guys know about work as it relates to force and distance? How is work? Work is equal to what? Middle school physics. Force times distance, right? Now what does that assume? It assumes that the force is applied directly in the direction of the displacement, the distance which is traveled, right? And also for that formula to make sense, the force has to be constant, right? Now, do you guys know about a spring force? Have you ever heard of spring force? Like if I have a spring, right, and I attach it to some mass m, right? And the equilibrium position is here. What direction does the force, like if the spring is in equilibrium when the center of the mass is through that dotted line, what's happened? The spring right now is stretched out, right? And Hooke's law says that the force is actually this direction, right? Pulling it back. So the formula for this, Hooke's law, is F equals to minus kx, where k is the spring constant. All right, k is a number that's characteristic of the metal with which the spring is made, right? Hooke was a contemporary of Newton that Newton didn't like that much. Like Hooke is nowhere mentioned in the Principia, which is saying something because the Principia is a very long and lengthy book. But if I understand history correctly, like Newton didn't care for Hooke because his arguments were more heuristic. They were less mathematical, and Newton was of the opinion that physics should be mathematical, right? So if you wanted to calculate the force done by a spring, right? If you wanted to calculate the work done by a spring, by the spring force, as it, say, goes from x1 to x2, right? Suppose that, this travels starting at x1 and going all the way over here to x2, right? Suppose that that's the motion we're thinking about. Could you use force times distance? Could you use force times distance for the force, for the work done? What would be the problem with that? See, we can't use force times distance over the whole displacement delta x, which is, x2 minus x1. Because the force is changing over that, right? In fact, the force is really radically changing. The force is pulling up to the equilibrium point, and then it's pushing once you're compressing the spring past the equilibrium point, right? So we can't use force times distance for this problem. But what you can do is go, okay, well, fine. What I can do is I can think about I can think about the spring going from, say x to, let's say, x plus dx, right? And I'm going to draw the box like smaller so I can. So imagine that you go from x to x plus dx, right? What is the work done in this little motion? The thing is, we can use force times distance there. Because over a very small displacement, the force is really not changing much. So it's not unreasonable to say the little bit of work done in that motion is just the force times dx. But the force here is Hooke's law, so we get minus kx dx. And so if I want to calculate the net work done for x1 less than or equal to x less than or equal to x2 for that displacement, for that motion from x1 to x2, I have to integrate from x1 to x2 minus kx dx. Now k is a constant, so we can pull it out. And you guys, tell me, how would I integrate x dx? What's the integral of x dx? It is 1/2, right, x squared. So I'm using fundamental theorem of calculus part 2, right? And so what we get is 1/2 k x1 squared minus x2 squared. That's the formula for the work done by the spring. Now, if you start from 0, right? If you start from 0, then the work is just what? It's just 1/2 kx squared, right? Yeah, if the starting point was the equilibrium. So like basically what that's saying is if you have a spring, right? And suppose it's at equilibrium, it takes the same amount of work to compress the spring over to here as it does to stretch out the spring over to there. So you store the same amount of energy, 1/2 kx squared, whether you go to here or you go to here. This would be x negative, this would be x positive in the usual system.
So another thing, should it be x1 minus x2?
Well, there's a minus out front. So, I guess it should be minus kx squared because of I said x1 was 0, and if x2 is x, it should be minus 1/2 kx squared rather. I'm wrong. Anyway, so this is not a physics course, but I think this is a useful example because it gives you an example of where, we write, and there's something that's true at the infinitesimal level, which we can't say at the macroscopic level, but we can integrate to bridge that gap. That's the idea of the infinitesimal method. Let me show you another example. Volume of a sphere. How would we calculate the volume of a sphere? Like 4/3 pi r cubed? Yeah. All right, so I guess I'm going to assume, oh well, I'm going to assume, that the area of disk is pi r squared, right? If you don't mind. That's something that's something I can't quite do in Calculus 1 because we don't have the right integration techniques yet. Like the integration technique to prove that is something we learn in Calculus 2. But suppose we know that, because you've been told that at least, right? And suppose you want to find the volume of a sphere of radius r. All right? So radius r. What you could do is imagine slicing the sphere up into disks, right? So you could take, like, call this direction here. What do you guys want to call this? What do you guys want to call the distance from the center of the sphere to the disk? We call this distance. We could use, let's use z, because in Calculus 3 we'd like to use z for that. Z. So the radius of this disk here, I'm going to call r, little r, right? What is this distance here to the center of the sphere out to this point? That is also big R, right? So I can take this triangle, sort of blow it up over here. So this is big R, this is the radius of the disk, this is z. So I'm just expanding, if you will, the triangle that's in the sphere. This right here. Now, what would the thickness of this disk be? How thick is it? Well, I'm imagining an infinitesimal disk, so I would say it's a little bit of z. So this would be dz. What's the volume? What's the volume of that slice of the sphere? It should be pi r squared times the thickness, right? So the height is dz, right? We know the volume of a cylinder works that way. This is basically just a very, very short cylinder, height dz and area pi r squared. Now, how is little r related to z and big R? How are these guys related? This is a right triangle, right? So what do we have? We have z squared plus little r squared equals to big R squared, right? Now here's the rule. To calculate, to actually use the infinitesimal method to add up the dv's to find the net volume, we have to express everything in terms of the integration variable. Here the integration variable is going to be z. So I need to take care of this r squared. I need to make it a function of z. Now, big R, this is just a number, right? But little r and big Z, little r and z are variables. So I can solve for that though, right? This is what? This is pi. Little r squared is really big R squared, right? Minus z squared dz. And so we got two options here. We can either use symmetry and say, like, the total volume of the sphere is double the volume of the top part, right? I think we should do that. So if we do that, we get the volume is double the volume of the upper half. So the upper half is from where? It's from this place right here, which is the equator, which is z equals 0, up to the top, the North Pole, which is where z is equal to big R, right? So essentially, I'm going to say, well, this makes sense 0 less than or equal to z less than or equal to r, this gives upper hemisphere, right? And so I should integrate from 0 to r pi times big R squared minus z squared dz. So that gives me 2 pi. Now what's the integral of r squared? What's the integral of z squared? Remember, r squared is just a number. So how does that integrate? We get r squared times z is the integral of r squared, because that's just like the integral of like 3 dz, which is just 3z. What's the integral of z squared? I'll put the minus in. The integral of x was 1/2 x squared. What's the integral of z squared? We add 1 and divide by that, right? Like, what is it? It's, you guys are going to make me do all the work. It's 1/3, right? What? You guys know it. You guys are, all right, 1/3 z cubed, right? And I got to evaluate that from 0 to r. What's that give me? It gives me 2 pi r cubed minus 1/3 r cubed, and then the 0 gives me nothing. What's 1 minus 1/3? 2/3, right? And so what's that formula there? You get 2/3 times 2, which is 4/3, right? So there it is, 4/3 pi r cubed. Now this thing I just did is, well, yeah, I mean, I proved that the volume of a sphere is 4/3 pi r cubed. Prove is maybe too strong a word. I've shown that if we know that the area of a circle is pi r, the area of a disk is pi r squared, it follows then that the volume of a sphere is 4/3 pi r cubed. But that's the nature of truth in mathematics. It's one thing implies another, you know. There has to be something which is basic also, which is assumed to be true, axioms. Now, so this is what Lab 6 was going to be on the infinitesimal method. I just wanted to spend, 30 minutes of class to show you this because it's an important idea, and more often than not, when we apply integral calculus in science or engineering, it's through this infinitesimal method. Like in physics, we add up things using integration. This symbol for integration is just a script s. It's continuous sum. Integration is summation. All right, so, but also I was just buying some time to make sure everybody was here and, ready to hear the next example. So I think we're there now. Everybody's here. Everybody's awake. So the thing I wouldn't test on this, right? Because in order to get good at these, you need to spend about a week on it and do a bunch of homework problems, all right? But you can calculate the volume of a cone, you can calculate the volume of a torus, you can calculate the volume of all kinds of three-dimensional shapes, provided that they're sufficiently boring that you can slice them with respect to, if you can find an axis through the volume such that the cross-sectional area is just a function of the coordinate along the axis, then you can integrate the volume of the slices just like we just did. And so you can calculate the volume of a lot of things like that if the thing is sufficiently boring. If you have some just sort of totally lumpy, messy chunk of clay that's got no kind of regular symmetry, then there really is no nice way to find the volume of that except to do a three-dimensional integral, which we learned in Calculus 3. But in Calculus 2, I think we'll come back to the volume idea. So, what is required in here, and I will test on, is finding the area between curves and calculating areas using definite integration, right? A lot of your homework is on finding the area bounded, by a function, right? But there's a couple of problems I mentioned last time that calculate the area between two curves, or area bounded by two curves, and I want to talk about that. And that's also this infinitesimal method. So it's the same thing again. So let's consider find area bounded by, I'll start with, I almost always do this example. This is a very simple example. Y equals x squared and y equals the square root of x. I'll start with this one. This one's a very simple kind of plain Jane example. So what is the graph? What are we looking at here? So x squared, well, it's like this, right? Square root of x is like that, right? And where do they intersect? It's like they intersect somewhere, right? And the area that we're asked to calculate is this kind of lemon wedge, whatever you want to call this shape here. That area. What is that area? All right, that's the question. It's clear what area is bounded, right? I think it's clear. So the point of intersection is the first thing we should try to figure out. What is that point of intersection? That should be where x squared is equal to the square root of x, right? So a lot of times students just tell me, well, that happens at 1. Because it's just kind of obvious, right? 1 squared is equal to square root of 1. But to derive it, we can solve this equation, right? So if you didn't solve the equation and you just put that was 1, I wouldn't take points off, But let me show you how to carefully derive that is the only point of intersection. I'm not deceiving us with my picture. In fact, there's 2 points of intersection, aren't there? Where's the other point? It's also on my graph. Yeah, we're here, right? So we square this equation. Then you've got x to the 4th minus x equals to 0, which is x times x cubed minus 1, right? So this either gives us x equals to 0 or x cubed equal to 1, which has solution x equals to 1, right? So those are the only 2 points of intersection. It really is just that. All right. Now, to calculate that area, I say, draw a typical approximating rectangle. Like here. I'm going to draw a vertical rectangle because it's just natural to slice this vertically, right? And I'll call the height of it h, and the thickness here will be, what's the thickness? It's dx, right? So dA is h dx in this case. And that's going to be true for 0 less than x less than 1, right? I know that because of the algebra I just did. I found the points of intersection. And, okay, fine. You're like, well, yeah, I could have seen that without the algebra. I can't argue with that. Maybe you could have. That's fine. What is h? H is y top minus y bottom, right? I'll say base since it's easier right there. So what's the top y? What's the bottom y? And does it make sense to say that there's just one of each? I mean, there is just one of each, right? The top y is given by square root of x, right? The bottom y is x squared, right? And then we use the infinitesimal method. We form the continuous sum of dA to get us A, right? A should be the integral from 0 to 1 of the square root of x minus x squared dx. What's the integral square root? Well, the x to the 1/2. 1/2 plus 1 is 3/2. 3/2. We divide by 3/2. We multiply by 2/3. So base. Yeah. I was going to write bottom in there, but I couldn't quite fit it. Base, bottom. I don't know. Oh, I got you. Is that Jack's open? Not yet. They're just teasing us with their commercials. The promises of inexpensive. Yeah, I mean, people are just going to go there for the ambiance, right? I mean, it's a happening, right? I mean, it's like, if Walmart opened back up in here again, we'd all be there, right? I mean, there was one here apparently, I've been told. What's that? Who deleted the Walmart? I did not delete the Walmart. I wouldn't delete Walmart. I mean, I have no such power. I mean, let's see here. So the integral of square root of x is 2/3 x to the 3/2. Integral of x squared is 1/3 x cubed, right? And we evaluate from 0 to, I love evaluating from 0 to 1. 0 to 1 are my favorite bounds because like 1 to the whatever power is what? It's 1. So you can just focus on the fractions. We get 2/3 minus 1/3. What's the answer? So 1/3. And that's so this if I was to shade it in, we just figured out that the area of this guy is 1/3. What's the difference between this and the kind of area problem we were working before? We were looking at the area bounded by y equals f of x and the x-axis, right? And the integral from a to b of f of x dx gives us the signed area, right? Here we're explicitly setting up like the dA to describe a typical, in this case, vertical rectangle we integrate over x. Let me show you another example. Suppose find area bounded by, let's see here, x equals to y squared minus 9 and x equals to 1. I think that would be, hopefully that'll make sense. So any of these find area bounded problems, like the first thing you have to do is you have to come to terms with what are we looking at. You need a picture, right, of what is the area we're trying to calculate, because that's what informs the calculation. So x equals to 1, well, that's easy enough. I won't worry about that. What's this x equals to y squared minus 9 look like? I mean, I can tell you some things. X is y squared minus 9. So that's y minus 3 times y plus 3 for what it's worth. So when x equals to 0, y is what? Plus or minus 3. Yeah, I mean, it's like, say, here or here, maybe. And what happens when y equals to 0? It's at x equals to minus 9, right? So what this is it's a parabola which opens to the right. You've got to think about the roles of x and y being interchanged. It's just a parabola that opens rightward. Like that, right? And what's x equals to? Well, x equals to 1, you know, that's just like in here somewhere. That's probably, I mean, roughly speaking, there's x equals to 1, right? It's a vertical line. So it's clear that we're trying to calculate this area, right? That's the area we're trying to calculate. So my question is, do you want to take the approach that we had in example 4? I would say no, we don't. The reason we don't want to take the approach in example 4 is because the same, like the top and the bottom y, they're both from the same equation, right? So it's kind of a pain. If we use the top and the bottom y, we're going to have to like use plus or minus square root, something like that. It's a pain. What's more natural here is to use horizontal approximating rectangles. So let me actually kind of smudge this out here. So we want to use like that for our dA, right? And before I get too carried away, what are these points of intersection here and here? That's from when what? When x equals to 1? X equals to 1, but x is also equal to y squared minus 9, right? So y squared is equal to 10, so y is equal to plus or minus square root of 10. So like this one is minus square root of 10, and this one up here is square root of 10. What's the thickness of my approximating rectangle? Although I really should say my infinitesimal rectangle. Horizontal infinitesimal rectangle. What's the area here, dA? Well, first of all, what's the thickness? It's dy. Very good. And this is what we might call W, right? So dA here is W dy, right? For minus root 10, less than or equal to y, less than or equal to root 10. But what is W? It's the, I say it's the right x minus the left x, right? Right minus left. So the right x minus the left x dy. And what's the formula for the right x? The right x is very boring. That's this one, right? So the right x is just 1. See it? What's the left x? Well, the left x is the parabola. So the left x is given from y squared minus 9. So I have to say 1 minus, parentheses are our friends, y squared minus 9. Notice that minus gives me a plus, actually. So we're left with, what is it, 10 minus y squared dy. So that's my dA, right? And then to find the total area, I take the continuous sum of the dA. I add them up to get dA, get A. A is what? A is the integral from the square root of minus 10 to the square root of 10 of 10 minus y squared dy. So how does that work out? Let's see here. So we're looking at, how's it go? 10y. 10y is the integral of 10 with respect to y, right? What's the integral of y squared with respect to y? Yeah, y cubed over 3, right? 1/3 y cubed. And of course the minus is still there, right? And I have to evaluate that from minus the square root of 10 to the square root of 10. By the fundamental theorem of calculus part 2. And what is it? Yeah, we have 10 times root 10 minus a minus root 10, right? Minus 1/3, 10 to the 3/2, minus 10 to the 3/2. Golly, run out of space. So of course that's 2 root 10, so we have 20 square root of 10 minus 1/3. I can peel out 10 to the 3/2 is 10 times root 10, right? So I can pull a 10 out of here, 1/3 times 10. And so that gives me, square root of 10 plus the square root of 10, actually, which is 20. So this is also 20 root 10. So I get 20 root 10 minus 1/3 of 20 root 10, which is 2/3 of 20 root 10. I mean, you could pull out your calculator and do this if you want, whatever. So I believe I get 40 times the square root of 10 over 3 if I haven't made an arithmetic mistake, which, I might have made an arithmetic. And when I've worked myself into a corner, the odds of me making an arithmetic mistake go up a lot. So. Any questions about this method that we're using? I think, yeah, the main thing is just coming to terms with what the area looks like in order to do the integration, right? So I'll let you guys try the homework problem, and then you can ask me about it Wednesday. How about that, yeah? A couple of examples for you. I think this was like problem, I can't remember the number now, but I said it the other class. I've unfortunately left my homework page in my other binder, so I don't have it on me. If you guys have any questions about homework, now is a good time to, ask them. I could work another area bounded problem if you want. Would that be good? It don't matter? One more. I'll work one that has got a little bit more sort of nuance to it. Let's say find area bounded by y equals sine of x and y equals x for minus pi over 2 less than or equal to x less than or equal to pi over 2. So this one here, we're going to have to think about some cases. Let me try to get us started. We know what the graph of sine looks like, right? Let's see here. So basically, here is the graph of sine from minus pi over 2 to pi over 2, right? It goes from minus 1 over to 1, right? Now, how about the line y equals x? How does that relate? Well, it's a line, right? So if we could find 2 points, then we can connect the 2 points to get the line, right? Where does the line y equals x end at? When you get x equals to pi over 2, you're at pi over 2, right? Which is like up here somewhere. Right? And on the other side, you're down here somewhere, right? And so y equals x connects those two, doesn't it? It was supposed to be a line. I tried. something went haywire over there. I should have drawn the line first and then added the endpoints, not the other way around. That would have been easier on me. So we're working on finding the area between sine and y equals sine x from minus pi over 2 to pi over 2. This is a little bit tricky because you notice how the tables have turned here, right? So there's two different places that you're trying to find the area, right? This side and that side, right? So over here, when we draw dA, right? dA is what? dA is equal to the top y, which is x, minus the bottom y, which is sine x, right? dx. But how about the flip side? Over here, dA is what? It's the other way around, right? It's sine x minus x dx. So for this kind of problem, where you have different cases, you have to break the integral up. You have to do a continuous sum over each of the cases and kind of add them together. That's the way you would approach this sort of problem. Now, I say that, but there's even a lazier way to do this one. But I'm going to write this out. So A is the integral from minus pi over 2 to 0 of sine x minus x dx plus the integral from 0 to pi over 2 of x minus sine x dx. Now, can you guys tell me how I can be lazier and like avoid half of the calculation here? What can you tell me about x and sine x? What are they? They're odd functions, right? They have the same, there's something very much related about to the right and to the left, right? So like if you look at this area right here, by symmetry, it should be the same as this area right over here, right? So I can double half of the calculation and get the whole thing, right? So which one would you double? I personally I like this one. So I'm going to say twice that. And then what do we get? So we have 2 x integrates to 1/2 x squared. What's the integral of minus sine x? Well, what function differentiated gives you minus sine x? How about just cosine, right? So plus cosine x evaluated from 0 to pi over 2. That's the fundamental theorem of calculus part 2. So I get pi over 2 quantity squared plus the cosine of pi over 2 minus, well, 0 squared, right? Minus the cosine of 0 over 2. So this gives me what? This gives me pi squared over 4. Cosine of pi over 2 is 0. Cosine of 0 is 1. So I get pi squared over 4 minus 1/2. There you go. I mean, I guess you can if you want to. You could write this as, I mean, is this more simple? It's 1/2 of 2, no, 1/2 of pi squared. If I factor a 4 out, I'll factor a 4 out. 1/4 of pi squared minus 2. I mean, is that more simple? I don't know. Whatever. Whatever you think, I mean, whatever's more simple to you. I mean, the latter answer is kind of nice because pi squared is essentially 9. And so 9 minus 2 is 7. 7 quarters. 7 quarters is about 1.75. Yeah, so, I mean, whatever. The first one is like 9/4 minus 1/2. It's kind of like 7 quarters. I don't know, whatever. I don't know. I got no dog in this fight. Never really been interested in dog fighting, by the way. But anyway, it's a side note there, personal note. Cat fighting, that would be interesting. Professional cat fighting. Like they do that for free without the presence of humans anyway. Like they just. You ever been woken in the middle of the night from cats fighting outside your window or something? It's kind of terrifying, isn't it? Okay, so I am now going to go back and give you more and more and more U substitution examples, all right? Because there's two things your homework is about. The one is calculating the area bounded by curves, and the other is calculating integrals using U substitution. And actually, I've already given you a pretty good slice of the non-trigonometric problems. So I'm going to actually focus in here on how to calculate the integral of various trig functions here. Okay? I suppose to do that best, I should really take a couple minutes to share with you my sneaky tricks for deriving trigonometric identities. And so most of these tricks are based on using what's called Euler's identity. So basically the next 10 minutes or so, I'm showing you secrets. Let me just call it secret trigonometry. Secret because people don't tend to teach it. So here it is. E to the I theta is cosine theta plus I sine theta. That means that e to the minus I theta is cosine of minus theta plus I times the sine of minus theta. But the thing is, cosine and sine are odd, are even and odd respectively. So like cosine of minus theta is cosine theta, and sine of minus theta is minus sine of theta. Right? So if you look at what I have then, and again, this is a formula called Euler's formula. And here I squared is minus 1. This is a complex formula. But if you take what I just underlined, and if you take what I just underlined twice, and you add those, what happens? See what happens when we add them? The I sine theta and the minus I theta cancel. We're left with twice cosine theta. If, on the other hand, I subtract them, I get e to the I theta minus e to the minus I theta, which is equal to 2I sine theta. So, therefore, if you know Euler's formula, you can easily derive that cosine theta is 1/2 e to the I theta plus e to the minus I theta. And sine theta is 1/2I e to the I theta minus e to the minus I theta. So I will continue to refer to these two basic formulas throughout the rest of my, let's call it, secret trigonometry. Now, you're like, well, who cares, right? Fair enough, who cares? Let me show you example 1, how this helps. Suppose you want to find an identity for cosine squared theta. Right? Cosine theta is, well, cosine theta is 1/2 e to the I theta plus e to the minus I theta quantity squared. Right? Using the boxed formula. Now, the reason that the boxed formula is, like, helpful is that the imaginary exponentials satisfy the usual laws of algebra. So I'll write it out. This is 1/4, and have e to the I theta times e to the I theta plus e to the I theta, e to the minus I theta plus e to the minus I theta, e to the I theta, plus e to the minus I theta, e to the minus I theta. I wrote it all out in glorious detail. There you go. So what's e to the I theta times e to the I theta? Well, that is e to the 2I theta. You add them, right? E to the x, you remember, e to the x times e to the y is e to the x plus y, right? This is still true when x and y are imaginary, actually. And so what's this? This gives us e to the 0. This gives us e to the 0. We get 2 from these two terms. And that gives us e to the minus 2I theta. So what we're looking at here is 1/2 plus 1/2 e to the 2I theta plus e to the minus 2I theta.
Okay, so because you say first of all that the previous step is saying e to the ei, it will be 0, right?
Mm-hmm.
Then e to 0 is 1. What do you
Yeah, e to the 0 is 1. Yeah. So can you tell me, what is this thing that I have here? Like, compare this and that. What is in the